All right, cool. So anyway, yes, we are going to dive into setting up the IBM account. So over here, what you guys should search is the IBM Quantum Experience. And then you can go to the first result over here and where it says, so actually, no. Before we do get started, does anyone here actually already have an IBM Quantum account? Put your thumbs up if you do. Okay, so I see Rodrigo and Benjamin. You guys already have and Joshua as well. You guys already have an IBM Quantum account. So for the three others that do not, let's run through a quick setup. And so what we'll do here is after going to the search result, we should go to new to IBM Quantum, create an IBM ID account. And where it says don't have an account down here, create an IBM ID. Is everyone able to get here so far? Put your thumbs up if you guys have. All right, Harsh was able to. Is anyone having trouble with it specifically, or no? It seems Alex was. What about you, Kalechi? Is that how I say your name?
It's Kalechi. Yeah.
Kalechi. Okay. You were able to get here?
Yeah.
Kalechi. Okay, good. And just go through the sign up process real quick. Is signing in with Google okay? Yes. You can use your Gmail or whatever home email you would like, or you could use your UTexas email. Either works, and you can do whichever one you would like.
Yeah, just use whatever works for you, because I think for this one, like there's no I don't think there are any IBM does any like deals or anything if you're a student, so it really doesn't matter which account you use.
It's all free.
Yeah. Yeah, so we can give you guys all a couple of minutes, maybe.
Yeah.
I think that's fair. Yeah.
Yeah.
Okay.
Once you guys are done, just put in the chat and say I'm ready to continue, or I'm done, or something. Cool. All right, cool. We should continue. I'll do the sign up process again, just to see where you guys are at. I'll just delete this account later. US. Okay. Yeah. Okay. And what you got to do now is you got to go to your email and verify. Have you guys all gone through the step or no?
I have.
All right, cool. Is there anything else that needs to be done after the 7-digit code? Do you guys know?
It just asked me about my interest and how much I know about quantum.
Okay.
It was like, you know, nothing. You have some basic idea. You have learned it in college, or you have a PhD. And I think that's all.
I see. Okay, cool. So
Yeah, that one is just like a survey to gauge what kind of people are using their platform.
I see. Okay. So everyone in here is in college, so you guys are all older than 16. So let's hit proceed, I guess. Please wait while we create your IBM ID. And you'll be, and so here's the end user agreement. just accept it. And accept and continue. And okay, yes, here's a short survey over here. I'm just gonna put UT Austin for mine. What is your familiarity? What's a qubit? I don't know, I'll just put whatever. What's a qubit? What would I like to use it for? Cool stuff. Because this is cool. And depending on what you guys want, you can check whatever boxes you want down here. These are all like product updates, marketing, etc. And yeah, so this is the IBM Quantum Experience. And what you guys should notice about here is that what you guys can notice is that you can have a quantum composer, which doesn't involve as much programming. You can literally drag and drop gates and run simulations that way. Or you can go to the IBM Quantum Lab, and that's where you do Python, and that's what we're going to do. And also, you may notice that you have this API token over here. And so what that's about is that you can actually take that token and put it into your quantum programs and run it on actual quantum computers, not just simulators. You can actually connect to like a quantum computer somewhere in the world, somewhere in Australia or Germany or New York or wherever they're located. You can actually connect to those and run them on those computers. So this API token will be useful later. But is everyone at this step? Everyone has their account now?
Yep.
Awesome. So, okay, good. You guys are signed in. And now what we will do is go over the first thing that we will work on. So we will go to the Kiskit textbook. And so what this textbook is it's a great resource to help learn quantum programming and the basic quantum computing concepts. And one part of this textbook is that they have labs. So you can go in there and they have experiments, and you can fill out those in like Python code cells similar to Jupyter notebooks and check to see if your answers are right. So we'll go here and check it out. So as you can see here, there are all these chapters in the quantum textbook, and this, honestly, all of this is a lot of material to learn. So we're probably going to be covering throughout the course of our sessions together, probably the first 2 chapters, 2, maybe 3, some of 3.
Yeah. One thing I wanted to add is like,
Yeah.
because it's clear from the survey that most of y'all are a bit like are less familiar on the quantum side, we will try not to assume any sort of prior knowledge, like ask about the quantum concepts, I guess, that are associated with the labs that we do, so that you can learn the programming on a quantum computer while like not being lost.
Yeah, absolutely. So right, and so over here we're at lab 1. And so what you can do is if you want to try this by yourself on your own machine, you can hit this over here and say open an IBM Quantum Lab. And what that will do is open the notebook in your IBM Quantum Experience. And you guys can see that all your labs are over here. And yeah, so this is where you can run the cells. But what do you think we should do, Ajit? Should we go over all of these? Should we go over the basic bit math, or should we go over how this works?
Yeah. Okay, yeah, let's get a show of hands. How many people know how the and OR gate work? Oh, and the NAND gate. Like, even know what it is fine.
I've ever heard of it.
Never heard. Okay, that's everyone actually. Okay, Great.
Okay, so all
Um,
you guys know what it is and know exactly what to do. So you guys know classical gates, that's definitely going to be helpful here.
Yeah.
So let's go over part 1 of the notebook, and or do you want to discuss adder circuits first, Jit?
So we could probably do part 1 of the notebook.
Okay,
Because especially because they already know what the logic gates are. So
cool. Yeah.
like it'll be easier for you to verify like what the quantum version of these logic gates looks like. So
Okay, awesome. So we start out with part 1, and we can do classical logic gates with quantum circuits. And so the goal here is to create quantum circuit functions that can compute exclusively OR, AND, NAND, and OR gates using the NOT gate expressed as X in Kiskit, the C-NOT gate expressed as CX in Kiskit, and the Toffoli gate expressed as CC-NOT in Kiskit. An implementation of the NOT gate is used as an example. So over here, it makes a basic program. It writes a subroutine, and you initialize a qubit over here. So you can do that by initializing a quantum circuit. And what this means is you have 1 qubit and you have 1 classical bit. And that's what this 1 and 1 means. And when you write qc.reset 0, you initialize the qubit at state 0. And now we're just going to quickly go over one example of, we're going to quickly go over how this gate actually works in matrix math. So where did JIT go? So I'll pull up a whiteboard and we can go over this. So I'll stop sharing and I'll start a whiteboard. All right, cool. So if we have a whiteboard here, so our qubit is initialized, hold on. So our qubit is initialized in state 0. So this is, have you guys been introduced to Dirac notation before? Okay. Is there anyone here who's never heard of Dirac notation in their life? Okay, so let's go over some basic Dirac notation then. So there are 2 parts to Dirac notation. We have what's known as a bra, which can be denoted like that, and you have whatever you want, say the letter A in between here. So that's what a bra is. And then you also have a ket. And that is denoted this way. Say you want to have A here. So this is Dirac notation, just basically how you write it. And what this means is, say, for example, you have a matrix or a qubit state that is, let's have the 0 state. So what this means is we have this 1x2 matrix. We have 1 and 0, right? If we want to take the bra of this, then what that means is you have to take the complex conjugate, which means, just in general, speaking in general terms, say, for example, you had a matrix 1 plus 2i, 2 plus 3i, 1 plus, I don't know what happened there. 1 plus 4i, 7 plus 8i. That's an 8, by the way. We have 1 plus 5i. These are all just random numbers, by the way. I'm just picking completely random numbers. But say we have any given matrix, right? So what you have to do is, if this is a supposed quantum state, then you take the complex conjugate of this matrix. So what you have to do is you have to reflect over like a square axis that's 3 by 3, because the horizontal dimension is 3. And so since this is a 3 by 2 matrix, this would become a 2 by 3 matrix. So instead, what you have is you'd have a 2 by 3 matrix, and each of these elements goes in, say, for example, we have 7 plus 8i, that is in 1 and 2. This would be going to 2 and 1. So we have 7 plus 8i over here. Or no, hold on. And also one last thing, you are taking the conjugate. So if there's a complex number here, it always turns negative. Each one of these turns negative when you put it in the 2 by 3 matrix, or sorry, the 3 by 2. So you have 7 minus 8i over here in row 2, column 1, and you have 1 minus 2i over here, and you have 2 minus 3i over here, and so on, so forth. So what you do to take the ket of 0 is you have 0 and 1. So you have, instead of it being a 2 by 1 matrix, you have a 1 by 2. So it would turn into 1 and 0. Is anyone lost or confused so far into how you change a ket into a bra? Everyone good? Seems there's some in the chat. Okay. Everyone looks like they're good. They understand. All right, cool. If you have any questions at all, don't hesitate to speak up. So basically that's what this is. If you guys want at any point, I'll take a screenshot of this, or this recording will be available, and I'll continue with the meaning of what all this means. So what the X gate basically does is, if you have a 0 state, it should be able to change it into a 1 state. And so basically what that means is, if our 0 state is 1, 0, it should be able to get converted into 0, 1. So this is known as the 0 state, and this is known as the 1 state. And so we should be able to have a matrix that should be able to do this, because in the end, all these operations is their matrices. And we use this matrix math, this matrix multiplication, to be able to convert quantum states. So in this case, the matrix which we use is, if we have our 0 state, we want to multiply by a 2 by 2 matrix, which is this over here. 0, 1, 1, 0. So this over here is known as the X gate, or the NOT gate. My writing is terrible, by the way. I'm really sorry, guys. And what this should be able to do is get you to 0, 1. So essentially, that's what's being done. All that is that it's matrix multiplication. So that's how the X gate works. So I'll go back to sharing the
Wait,
quantum.
I have a question.
Oh, yeah, sorry, what's
Um,
up?
I thought that the first matrix is 2 by 1 and the second is 2 by 2, and so that we can't multiply them.
Oh, yeah, it's on the left. The multiplication should be like, it should be left multiplied.
Oh, oops, sorry, then these two should be switched around. I'm very sorry, guys.
Okay, that makes sense.
Yeah, okay, yeah, they are being multiplied by each other. It's just the other way around. I'm so sorry. But yeah, so let's continue on with the notebook. So let's get back here. Share screen. Yeah. Okay, so basically all that this is doing is we have a NOT gate over here, right? So the comment is saying if we encode 0 as the qubit, so we can either encode our qubit as a 0 or a 1. And since the qubit is initially 0, we don't need to do anything for an input of 0. But for an input of 1, we need to have an X to rotate the 0 or 1. So that's basically what the NOT gate is over here. So let's say, for example, let's run this code cell. If we have this, then I should probably run this first. Okay, that's better. And what we can do is now we can test this output. So just give it a minute to run. Okay, so what this basically does is it draws the circuit. So we initialize our qubit to have a state of 0, and we want to have a NOT gate, and then we take the measurement of that NOT gate and output it to the classical bit. So oftentimes what happens in Kiskit is once we are done measuring and once we get our results, we have to output the results to classical bits so that we can measure them appropriately without their state collapsing. And so this is for the 0 state. And if we have a 1 state, then we have two NOT gates, which should. So if we have a NOT with input 1, that should give us an output of 0. So this tutorial honestly is weird. Are you guys following along with this, or are you guys a bit confused?
I'm following along.
Okay, you guys are following along? Okay,
Yeah.
good. If you guys have any questions, don't hesitate to speak up.
Yeah, I have a quick question.
Yeah, what's up?
What does that last black box mean?
This last black box, this means a measurement. So what that means is for qubits, what you do oftentimes at the end of experiments is you measure them and you output the result to a classical bit. So you can encode the quantum data as classical data and continue with whatever operations you need to in classical bits. Because oftentimes many use cases for quantum computers happen with classical computers. They work in conjunction in a hybrid system, sort of. So what Kiskit does is it has a built-in way to be able to convert quantum data to classical data.
Yeah.
So, yeah. So this is just classical logic gates with quantum circuits, and this is our basic NOT gate. And now we have an exclusively OR gate. So what this means is it takes 2 binary strings as an input and gives 1 output. So the output is 0 when the inputs are equal. And if the inputs aren't equal, then we should be getting a 1. So if we have an XOR gate, what we need to have is if our input is 1, we need to apply a NOT gate once again. And if our input 2 is 1, then we need to apply. So Yeah, we need to apply it to the second qubit. So over here, we're referencing the first qubit, and over here, we're referencing the second qubit. Are you guys following so far?
Yeah.
All right, cool. And so what we're going to do now is we're going to draw the circuit. So this is the function over here. And so if we want to test the function for input 1, if we have 0 or 1, and for input 2, if we have 0 or 1. So if we have QC comma output, and then we apply our XOR operation. And so if they equal each other, we should be getting a 0. And if they don't equal each other, we should be getting a 1. So that's basically what that does. So over here, it says XOR with input 0, 0 gives us this output. XOR with inputs 0, 1 gives output 1. XOR with inputs 1, 0 gives us an output of 0. And XOR with both inputs being 1 gives us an output of 1. So we applied the NOT gate respectively where we need it to, and the quantum operation takes care of the rest. Oh, okay. Also, I would like to show you guys one thing. So in order to run an experiment in a Kiskit simulator, what you'll have to do is establish a backend. And what that means is you can either choose this to be a quantum simulator, or you can choose this to be an actual quantum computer. But for now, the most basic we can have is an air simulator. So whenever you guys run your experiments, you should declare this line as your backend. And in order to have a job, you should have a quantum circuit and a backend to run it with. And a shot is the amount of times you run the experiment. I'm not really sure what this parameter means over here. Do you know what that means, Ajit? Memory equals true.
I think that's like, if your program like will have a state, then you're gonna want to have memory so that it's stateful.
Okay.
But in our case, we won't need it because we're just adding circuits together and stuff.
Cool.
So like, it doesn't really matter if there's a state, right? In our case. Yeah.
Okay. And yeah, so this is our job. And once we run our job, we should take the outputs from our job, and we can return that as part of our subroutine. So first, what these guys are doing is they're taking the inputs, drawing the circuit accordingly, and giving us the output over here. So that's with the XOR gate. And now we move on to the AND gate. So what we do is we can take 2 binary strings as an input, and we can give 1 as an output. So when both of the inputs are 1, we give an output of 1, but any other case equals 0. If both the outputs are 0, the output is 0. Or if qubit 1 or 2 is 1 and the other is 0, then it will also give an output of 0.
Hey, a quick question.
Yeah, what's up?
Do I need to type something in the XOR? Because it's not like working. Like 1, 0 should be 1 and 1, 1 should be 0. Right?
In XOR?
Yeah.
XOR is short for, wait, I'm sorry, what was your question again?
Isn't there code we need to write? Because it's not like working. Like, shouldn't a 1, 0 give a 1 and a 1, 1 give a 0?
Over here, so hold on. Over here is the picture, and it's outputting over here. So our output is this, and if we have, so that is weird.
If there's a spot that says this is where
Yeah.
your program goes, like I think we need to fill it in.
Oh, okay. So this is testing the function over here, but this is where your program goes. This is for the AND gate. So, okay, yeah. So I guess over here we have to fill out for XOR. So they do it for us up there. And I see. Okay, so we have to, yeah. I'm sorry, I didn't see that before. Thank you for catching that, Benjamin. So we can do this real quick. So this is where your program for the XOR gate goes. So if you have the input as 1 and the input.
Yeah, we would just kind of replicate the one above, but instead using a CX gate, right?
Exactly, yes. So yeah, you're doing a control. Yeah, you're doing a control NOT gate over here. So yeah. Would you guys like to try this on your own, or would you like me to do this right now? Type in the chat.
Yeah, I think someone said, could you show it?
Okay. All right. You guys. Okay. So all you basically have to do is, if you want. So we should just be able to apply a CX gate here. To I think that's how it should work. And let's test it out. Yeah, so basically all you had to do is type in 1 line of code and it should give you, and it's known, the control NOT gate over here is known as C NOT, and you can apply it to both qubits. So what you do is you have, if you have both zeros, you should be getting an output of 0. And if they're different, then you should be getting an output of 1. So yeah. All right. And the AND gate. So I think we'll work through this. So we take in 2 binary strings over here and we give 1 as an output. I know I read that before. And it wants us to. So I'll try this one as well for you guys. So oh man, I'm forgetting. Okay. All right, guys, please forgive me this once, but I'm really forgetting, and I did physics homework before this. That was absolutely killing me, so I'm just going to look it up really quickly. Okay, so over here, we use the CCX gate in this case.
Confusing because they changed the name to the Toffoli gate.
Yes, the Toffoli gate, that's what it's known as. Should be able to work. All right, cool. So over here, if we have AND with input 0, 0, we should be getting 0. If we have inputs 0, 1, and 1, 0, we should be getting 0. And if we have 1, 1, then we have an output of 1. So that's the AND gate. And we also have the NAND. And so finally, the final one in this, the final 2 are the NAND and the OR. So our goal here is to take in 2 binary strings and give 1 as output. The output is 0 only when both the inputs are 1. So over here, we can do a single operation again. Should say up here that we can use All right, so if we want QC.NAND, then we can try 0, 1, and 2. Okay, NAND isn't a function. Do you know which one I should be putting, Ajit? I don't think I remember this one.
Oh, so yeah, I would have to look at the documentation.
Do you need 2 gates for this?
Yeah, I think you do need 2 gates for this.
I'm guessing it's
'cause you just do and then you do not. So,
Okay.
Yeah.
Okay,
So I think
okay, and not. That would mean I can copy this one from the previous tutorial. So that's CCX and then I do a not, right?
yeah,
Or,
like this method
yeah,
already gives you an and, so yeah.
it's, oh, oops, that should be an X, sorry. Okay. No, that should work. X, it's weird.
Oh, wait, X only takes 2, I think.
Oh, right,
Yeah, it only takes one actually.
okay. So let's do for 0. So we have 0, 0 giving an output of 0, a 0, 1 giving an output of 0, a 1, 1 giving an output of 1, and a 1, 0 giving an output of 0. That's how it is supposed to function. All right, thank you, Ajit. All right, and for the last one, we want to make an OR gate. So it takes in 2 binary strings and gives one as an output. And if either of them are 1, then if either of the inputs are 1, or if both are 1, then our output should be 1. So we can do this with, I think we should be able to do this with, do you know which one this is for? Again, Ajit?
This is an OR gate, right? So
Yeah, I think it's just the opposite of this. It's
yeah,
just-
that sounds right. Yeah.
Yeah, it's just the opposite of this. So should be this with an X on qubit 2, right?
Yeah.
Should be it. Oh,
Wait, was this supposed to be an OR?
yeah, this is supposed to be OR.
Yeah, I think 1, 1 was supposed 0, 0 should be outputting 1 and 1, 1 should be outputting 0.
Yeah,
Or 1, 1 should be outputting 1.
Hmm.
But I think here everything is just outputting 1.
yeah. Let's try that. That's weird. All right, I should check how to do this one. Is it just a controlled X?
For an OR,
Yeah,
I think.
hmm.
Maybe we can just do this next time since it's almost 2.
Yeah. Okay, so We went over 3 of them, and what we will assign for you guys next to do over the 2 weeks is to find out this OR gate part, and also to do part 2 of this notebook. And if you guys have any questions, you can drop it in the Learning Labs Discord channel. And are there any final questions about this?
Oh, we also encourage you guys to use the channels because
Yes.
one of the main aspects is collaboration, right? So
Yeah.
you're all in the same Discord group, just send a text in the channel and respond to each other so you can try to figure this out.
Yeah, and we're always here to help you too. So any final questions?
All right.
Get the answer. Do you want us to post it, or next time we'll go over the answers?
Please post it.
Okay.
And yeah, what was your question, Ben?
I'll put something about this in the chat, but can you scroll up to the NAND again? What did that look
NAND.
like? I
NAND is right here. I think it's this one. Yeah, NAND is right
Yeah.
here.
What did the output for that look like again?
The output is, it gives 0 for everything except when it gives 1, 1.
Isn't that what an AND gate does?
Oh, yeah.
Shouldn't it be the inverse of that?
Yeah, I think the or.
Oh, snap. Yeah, you're right.
Oh yeah, but we
think-
could just add an X at the end of all of the other, at the end of the output. And
Okay.
then that'll flip it.
I think
Yeah.
it needs to go in 2 or something. Yeah.
Yeah, the outputs for or, I think, resembled that of an AND gate.
Yeah. So we have 1, 1.
Yeah.
Yeah, so this is a NAND gate. And yeah, so you guys are right. This is a NAND gate. Let me look at the other ones to make sure they're all right. So AND should be 0, 0, 0, 1. Right. And then we have exclusively OR, we have a single controlled NOT gate. All right. So yeah, once you guys find the solution for OR, please post it in the Discord channel. And when you guys have the time, try to go over part 2 if you can. I know we all have really hectic schedules, but try to look over part 2 for next time. Any final questions? Anything more? All right, guys. All right, I'll take that as a no, but thank you guys all for coming, and I'm sorry about having to look up all the gates, and I'll do better next time at that. But I'll stop the recording and I'll send this all out to you guys.